All right, a little more on the expectation of functions of a random variables. So here's the theorem for you. The expected value of, let's say, the sum, k goes from 1 to m of a sub k times some function, say g sub k of x1, x2, etc., xn. This can be written differently. First of all, what is all this? Take a look at this. Maybe you've got a bunch of these random variables, and g sub 1 is some cost that's associated with them. Okay, maybe it's these are inventories of items or something. And maybe you multiply this cost by some number, some constant, and then maybe the total cost is actually the sum of all that plus some other function, you have some other kind of cost that's associated with these variables times a constant. And you have this over and over, and you're adding up the total cost is the sum of all these costs. You want to find the expected value of all of that. This just turns out to be, it's not hard to show that this is just the sum k equals 1 up to m of a sub k times the expected value of g sub k of x1, x2, etc. Okay, so it's not hard to prove, just using the basic principles of expectation. Okay, the definition of expectation. So you might try that. Here's another theorem that I will prove partly for you. If x and y are independent random variables, and let's say, let's say g and h are functions, then the expected value of g of x times h of y is just the product of the expectations. Oops, it's an h of y, like that. There we go. Okay. Moreover, or more generally, if x1, etc., up to xn are independent, mutually independent random variables, then the expected value of the product of, let's say you have a function g1, you have g2, g3, all these functions. K goes from 1 to n of 1 to m. Oops, 1 to n, I guess. This is just going to be the product of the expectations. Okay. It's quite nice. So I'm going to prove this. I'm going to prove this first part, and I'm just going to restrict myself to the continuous case. The discrete case follows analogously, except with summation signs. And in fact, if you look at it the right way, the continuous case actually sort of, what we're about to do with the integral signs, it's easy to see that the discrete case is the same. Okay, so proof. So I'm going to start with this expectation of the product of those two guys. I can write this as the integral over the reals of g of little x times h of little y times the joint density function for x and y dy dx, right? Yeah, because I'm wanting the expected value of the product of those two functions, right? So you already know how to take expectation of anything. You just integrate it with respect to the proper density functions for all the random stuff, right? All right, but now remember x and y are independent, right? Since x and y are independent, I can write this as the double integral g of x times h of y times f1, or let's say f sub x of x times f sub y of y dy dx, right? Since they're independent, I can write this. I can write the joint density function as the product of those two marginal density functions. Okay, and so now I tell you what, I'm going to group all my y stuff together. And let's see, none of this x stuff depends on y. I'm going to go ahead and pull the g of x stuff out and the f sub x of x stuff out. I got this, right? Times h of y weighted against f sub y of y dy, and then if that's through, I'll have dx, right? Now, all of this stuff, this integral here, is just what? It is the expected value of h of y. Okay? So, this is integral over the reals, g of x, f sub x of x, times the expected value of h of y dx. Now, this guy right here is a constant. That's right. It's the expected value of a function of a random variable. It's a constant, so I'll just pull that guy out, and I get it's the expected value of h of y times integral g of little x times f sub big X of x dx. Right? But then guess what? All of this stuff is just the expected value of g of x. And so, in fact, this whole thing is done. It's the expected value of h of y times the expected value of g of x. Very nice.